Okay, so here's our introductory lesson on accuracy versus precision. Just to give us started here, physics. Some of us have studied physics before, some of us haven't. Physics is the study how the universe works. Okay, for the most part, we're going to be studying how the properties of matter and energy and relationships between them and how they all work together. Okay, it's a different kind of science. It's a very much a mathematical science. So we're going to be doing a lot of math. Okay, especially now in the online environment for this class. We'll be doing some demos, some labs we can see from apps, some flash apps or something like that I can find, some videos to demonstrate our demos. But we're not going to be doing it a very highly lab-oriented physics class for the summer program. So moving forward here, physics is still a science, so it's still both science and math, but it's a bit of a mix. In general, there's two classifications for sciences. Experimental physics and theoretical physics. Again, experimental deals with experiments. Theoretically, more math, more science, more writing things down and thinking our way through things. There's a big difference here between the two in how science is going to be working or how physics works nowadays at the university or past the high school level. There's a big difference between a mathematician and a physicist. Boils down to what we are doing. Math just plays with numbers, where physicists are playing with measurements. Okay, so we have to be very, very careful how we define a measurement. We're going to be doing this two different ways today, or talking about it through the next couple lessons here. Measurements come in exact quantities or exact values, counting how many people are in the room, 32 people, or a defined value that we set, like 100 centimeters equals 1 meter. It's defined. We don't have a choice on what that means. But measurements are never really exact because of the uncertainties and the errors. Are we actually measuring 5.2 centimeters or are we measuring 5.7 centimeters? A little bit trickier to be careful of, and that's where we have to be much more careful is how we define a measurement. So we have two different ways of doing this. We have precision, which describes the exactness and repeatability of a set of values. Precision is like decimal places. It's how many decimals are we accurate to. Okay. Whereas accuracy describes the degree to which the results of an experiment or calculation approximates its true value. So if we wanted to measure 10, how close is another measurement to 10? Is it 9.5? Is that good enough? Or is 6 better? So that's the idea, is how close we are truly towards a real value of 10. Okay, so precision and accuracy, we're going to use these words very clearly. When we're dealing with physics, we have to be very clear on our language and what words we're using. So as an example here, we're throwing some darts at a dartboard, and you can see the darts being thrown at the dartboard have all been situated in this area of the dartboard up here. We missed. We entirely missed. However, all of the dots themselves are really close together. So what we say is we have good precision. All the hits are close to each other. But we have poor accuracy. Poor accuracy coming by, it's not on center. It's way off of what we were hoping to get. Okay. More results here, and we can see how these are going to fly out here. On the next ones here, they're not clustered, so we have poor precision on how this is going to work. This is poor precision, but maybe good accuracy? Hard to tell. Very hard to tell how we're going to save that. Are we accurate or not? They look kind of clustered around the center, but it's not a very good example. It's very hard to tell. And the last example we can kind of see here, we have very good precision, and we are pretty accurate. We all got it near the bullseye there at the beginning or in the middle. We can see the accuracy, and we're all clustered together. Each shot itself, repeatability of the experiment, is that it's really close to the center. So we can look at it in terms of numbers now. Which is more precise, a 12.74 centimeters or a 127.4 centimeters? Which is the more precise measurement? And we can see an answer for that one there. It's decimal places. Well, 12.74 is way more precise. We're not concerned with accuracy because we don't know the true value of what we're trying to measure here, but we are measured with the precision. We used a really good ruler and we got 12.74 centimeters. This time, though, we're setting up an experiment. We're measuring temperature of which water boils. Now, as we all know, or maybe we don't know, but water boils at 100 degrees Celsius. So we set up these containers of heat, and we put the water on the heating pads to boil. We do this 5 different times. We get results of 67, 68, 68, and 65, and 66. We see 5 different results. Now these results themselves are very close to each other. Because they're close to each other, the precision, the instrument itself, is not doing too badly. We're getting good, precise results. But are any of these near 100 degrees Celsius? So we're missing our accuracy. And that's exactly what's happening here. We are precise. The measurement of the device is okay, but something else is wrong with the experiment. We're nowhere near the actual measurement value of 100 degrees Celsius. In general, I don't know how much we're going to use this over the next month, but it's more for lab scenarios. When we're working on measurement types or measurement errors, we have things like random error affecting the precision of results. Sometimes something goes wrong in a lab. We've got to fix that. We can fix random error. We can fix the precision of it by using a better measurement instrument. So instead of using a 30 centimeter ruler, we're going to use a 10 centimeter ruler, or even better, we're going to use a laser micrometer or something like that to measure a better length measurement. Okay, so devices. A random error comes from any variations in the experiment itself. And finally, the last thing here is we have systematic error, and that's what's affecting accuracy. Systematic error is reproducible. It's going to keep going. It's going to have the same error every time we do the lab. As we saw with the degrees Celsius, with the temperature lab earlier, or the temperature results earlier, systematic error, if we could fix the lab to get near 100 degrees Celsius, then we would have been pretty good. So systematic error is usually fixable, and it is affecting the accuracy of an experiment.